Hello, good morning. Mhm. Okay. 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 Hello, good morning.
गुड मॉर्निंग मैम
कौन बोल रहा है?
Good morning, ma'am.
अली जुल्करनैन मैम
Zulkarnain. How are you, Zulkarnain?
आई एम फाइन हाउ अबाउट यू
Thank you. और कौन बोला था अभी?
अबू बकर मैम
Rana Shahbaz, ma'am.
Hello, Rana Shahbaz. Hello, Abu Bakr. Who else is there?
अस्सलाम वालेकुम मैम
Walaikum salam.
Mohammed Bilal, ma'am.
Muhammad Bilal. How are you, Muhammad Bilal?
इब्राहिम
I'm
रिफान
fine.
Ibrahim Irfan. Hello. Okay, so who else do we have? Amelia, hello.
Yes, ma'am. Good morning.
Good morning. Arisha,
Good morning, ma'am.
good morning. And we have Fariduddin, hello.
Good morning, ma'am.
Good morning. Sania,
Good morning, ma'am.
good morning. Chand Khushi,
Good morning, ma'am.
good morning. Who is this? Abira. Hello, Abira. Okay, Abira, are you there? So I don't know where is Abira. She's showing in the list. ये तो नहीं log in करके गायब हो गए. So anyway, so let's start. I have shared this PDF with you. You can see it, right? ठीक है? Okay. Yeah. Okay, can you see the PDF?
Yes, ma'am.
Yes, please. बोला करो ना. So I have to confirm कि आपको नजर आ रहा है, and then we can start working on it. Okay, so the topic we are going to talk about today is going to be potential energy and conservation of energy, right? You're familiar with energy. We've been talking about it, right? And you're also familiar with potential energy. So let's just recap what we did. So what do you understand by energy? Will somebody answer that?
Ability to do work.
Ability to do work. And what kinds of energy can we have? What kind of energy have you come across previously?
Kinetic energy.
potential energy.
Right. Kinetic energy, potential energy. So what is kinetic energy?
Energy due to motion.
Motion, right? What's the formula?
1/2 बल्कि ये नहीं था.
Kinetic
1/2
energy
mv square.
is equal to half mv
Mv
square.
square.
And this v represents velocity, and therefore this is related to motion. So the energy due to motion is known as the kinetic energy, right? Now we are going to talk about potential energy today. So what is potential energy? Can anyone explain this?
Energy
Ma'am,
due to
Ma'am,
height.
stored energy.
Okay, one person said stored energy. Anyone else?
energy due to position.
Yeah, this is
Change of
basically
position.
energy due to position. Can you give me an example?
Water stored in dam.
Yeah, very good. So hydropower is an example, is a very good example of the concept of energy, the concept of conservation of energy, and then potential energy and kinetic energy. All of these are applicable in that case. So let's come to conservation of energy. What is conservation of energy? Conservation of energy means yes, someone bolo.
A kind of usage of energy.
No, it's not.
Ma'am,
No.
that energy cannot be created nor destroyed. It can be transferred from one to another.
Very good, Fariduddin. So yes, it is that the total energy of the system remains constant. It can change from one form to another, but the total will remain constant. For example, if we look at the example of a dam, you know that you have a height and water is falling from a height. So at a height, the position is higher, and therefore you have a potential energy. This potential energy, as water falls down, it gains velocity, and therefore this potential energy changes into kinetic energy. And as you go further, you will see that this energy will then be used to turn a turbine. And when you're turning a turbine, this is again an example of mechanical motion and hence mechanical energy. And this turbine then produces electricity, which is a form of electrical energy. So you see that energy can always change from one form to another throughout the whole process, but the total energy in the system remains constant. And this is the law of conservation of energy. So that's why when we say that we have, for example, a shortage of energy, and we are going to produce energy, that's not exactly correct, because we are actually finding means of converting energy to a form that's usable for us. So we need to, for example, there's a lot of energy in the world. For example, the sun is a source of great energy, but we have to find a way how we can bring it into a utilizable form that we can use. So it's the conversion of energy that's always important. And otherwise we do have energy, the total energy in the universe will not change, right? So that's the basic concept. But today we are going to concentrate on not the electrical kind of energy, but we are going to concentrate on mechanical energy. So examples of mechanical energy are potential energy and kinetic energy. So we did talk about the kinetic energy last time, so today we are going to talk about potential energy, right? Okay, so you can see, let's start with how we are going to define this. Potential energy in this book is being defined by the symbol capital U. Just as I said, in some books you also have PE written for potential energy, but again, like here in this case, we have capital U. And then there are different kinds of potential energy. So the energy that we talk about, for example, where you take an object to a height and therefore it possesses an energy which is a potential energy. This is known as gravitational potential energy, because this is due to the gravitational force, right? And then the second example, like we studied in the last case, was the spring mass system. So when you have a spring mass system, for example, the energy, potential energy, like we talked about the examples of a watch, and also this principle is used in some toys and so on. This is elastic potential energy, whereby when you compress a spring, it stores energy, right, due to its state of compression or extension of an elastic object. So elastic object can be a spring, for example. So these are the cases of potential energy that we will be talking about in this case. And now here you can see that energy is always related to work. We know that when we do work on a body, this work is stored in that body in the form of potential energy. So for example, when we were winding the watch or the toy, when we are compressing the spring by turning the screw of that spring, and when we are doing this, we are storing potential energy. So here you have a simple example in which an apple is thrown upwards. So when you're throwing a body upward, you do some work on this body which is against the gravitational force, and therefore this is negative work, and this work will be stored in this body as potential energy. And then when that body is at a height, when it falls down, that body will do work, and this will be known as positive work done. So these are the conventions of when you're going to take work as negative and when you're going to take work as positive. Again, this is due to uh, in a vertical direction, and therefore it's because of the gravitational force. And since potential energy is due to the work done, therefore we have this equation: delta U is equal to minus W, where minus W is the work done and delta U is the change of potential energy. Okay, so delta we know always represents potential energy. Also, this work done is due to the gravitational force, and hence it's represented by Wg, but then the general expression would be just W. Okay, and also when you're talking about a spring block system, the potential energy will be known as a elastic potential energy. Otherwise, it will be known as the gravitational potential energy. Okay, this is a tomato, it's not an apple. Okay, anyway, so a tomato is thrown upwards, and as it rises, the gravitational force does negative work on it and decreasing its kinetic energy. As the tomato descends, the gravitational force does positive work on it, increasing its kinetic energy. So initially, the kinetic energy was greater. Gradually it converted into potential energy. At the top, the potential energy is greater. So here you have the potential energy maximum, and here you have the kinetic. In the middle you have kinetic energy plus potential energy. Gradually this energy is being converted into motion, and therefore you have a kinetic energy component. But when it reaches the maximum height, the velocity becomes zero, and then the energy is completely potential. And then when it comes down, the potential energy decreases and the kinetic energy decreases. So energy is changing between one form to another, but the total energy is always constant. So this is what we are talking about. Now we can look at the mass spring system as well, which is another example. And in this case, you know that if you have a spring and a block attached to a wall. In the last chapter, we were talking about the wall on the left side and the spring on the right side. In this case, they have reversed the direction. But anyway, you can see that this is moving in the horizontal direction, and hence you have the x-axis. Now, when you're pushing this towards the right, so always draw a diagram, or if a diagram is given, you follow that diagram in order to get your concepts and equations correctly applied. So in this case, if you're moving it to the right, you're compressing the spring, and if you're pulling it to the left, you're extending the spring. Okay, so in this case, the initial position is a rest position, which is at x is equal to 0. So when the displacement is 0, which is here, this is known as the mean position, and it's also known as the rest position. It's known as the rest position, or it's known as the 0 position, or the mean position. So again, you will come across these expressions. It's known as the rest position, the mean position, or the zero position when the body is not moving, it's at rest and no force is being applied on the body. So when the block moves rightward, as is shown in the first case in figure A, you see that negative work is done on the body. Okay, so when it's moving, we will say that work is minus W when it's moving towards the right, and then when we pull it towards the left, we say that the work is positive W plus W. Okay, so these are the conventions that we are following. Now, again, looking at these examples, we have the concept of conservative and non-conservative forces. So, we have studied the example of the tomato, or it can be an apple, or it can be a ball, whatever. And that's the example of the gravitational case. And then we have studied this case of a spring mass system, right? Now, when the system configuration changes, the force does work called W1. Let us say that the initial case, state 1 of the W1 corresponds to state 1 of the system. State 1 can also be called an initial state. Okay, so sometimes we use the symbol I and we can use the symbol 1. So in this case, they're using 1 to represent the first state of the system. And in the first state of the system, you transfer an energy between the kinetic energy, which was represented by K, and it changes to another form of energy. Now, you can reverse this as well. You can see that the case of the gravitational example, the energy that was gained can be reversed. Okay, and also in the case of the spring, the energy that was done in doing this work can also be reversed. So when a system can be reversed, the energy transfer in the second state will be W2. So one state is 1 and the second state is 2. The 2 can be the final state, you can say, or the second state. So this can be the first state and this can be the second state. In both situations, we see that the work done is equal and opposite to each other. So W1 is equal to minus W2. When this is the case, this system is said to be a conservative system, and the force applied will be called a conservative force. So examples of conservative force are the gravitational force and the spring force. Both of them are conservative forces because we can reverse the change that has taken place. A body that has been taken upwards can also be brought downwards. Similarly, a spring that has been compressed in the right direction can also be extended in the left direction. So we can do work in both directions and reverse the state of the system, and hence this is known as a conservative system, and the force is known as the conservative force. The second case is a non-conservative force. A non-conservative force is for a system that cannot be reversed, and examples of this are frictional force, thermal energy, frictional energy. In these cases, we cannot reverse the work done. So sometimes we also say that the energy has been wasted, okay, in that case, but it's not really stored in that case. So these are examples of non-conservative forces, and these can include the kinetic frictional force that we talked about, which was small f is for friction. And what kind of friction? If it's due to motion, so then we represent it by a small subscript k, and it's called kinetic friction. Similarly, the drag force is also that we studied previously, which was represented by a symbol capital D, is also an example of a non-conservative force. Similarly, a thermal energy, for example, heat is produced whenever there's friction, and therefore this is also related to the non-conservative force. So when only conservative forces are acting on an object, we say that we can simplify it and solve the problems, right? So now coming to the path independence. For conservative forces have the property that the work done does not depend upon the path followed. So for example, if you have to take a body from point A to point B, you can follow any path, but the work done will be the same. So for example, you can go through this path, or you can go through this path, or you can go through this path. The work done will always be the same. It's independent of the path, and therefore this is known as a path independence of conservative forces. But also, as a consequence of this, we can also say that work done around a closed path, around a loop, if you start at an initial position A and you perform work to go around and come back to the same position, this is a closed loop. It's called a closed path, and therefore the work done in a closed path is zero. So this is another definition for path independence. So the net work, the total work done, although in different parts you can calculate the work done, maybe W1, W2, and so on. But at the end, if you add all of those works, like when W1 is equal to minus W2, when you add them, you have W1 plus W2 will be equal to 0. So the work done along a closed path will be 0. Now, this is shown in this figure. You can see in this figure that you have 2 points A and B, and so you have followed the path 1 and you followed the path 2, and in the end you can say that the work done was equal. So WAB1 and WAB2 was equal but opposite to each other, and therefore when you add them, they cancel each other and the total work done will be 0. Okay. Now you can come to the equations for the work done. As you remember previously, the equation for the work done was work is simply equal to force multiplied by displacement. You remember this, right? But then when we talked about a variable force, we had to divide it into small parts and then calculate over each part and then make a summation sign. So we had something like this. But then when we have a large number of these points, we take a limit, which is x tends to 0. So since the work is being done in the horizontal direction, we take, instead of d, we can take x. So force becomes a function of x. And then we can write w is equal to an integral starting from a point 1, which is x1, to a point 2, which is x2. And force is a function of x. And it will be in, ye kaun kar raha hai? Rana Shehbaz, stop.
मैम आई एम सॉरी गलती से हुआ था
गलतियां ना करें, please. Okay, so this becomes the equation of the work done that we studied in the last chapter. So this is the same equation we have here. So this equation, since we know that the change in potential energy is, the change in potential energy is equal to the minus negative of the work done. So therefore we can write delta W is equal to minus of this equation, and this is how you get this equation. So these are the two equations for work done when you have a variable or a changing force. Okay, now you are familiar with gravitational potential energy. This was the example of the tomato that you were throwing upwards. So you have an object here that you threw upwards, and in that case the work done in this case depends upon potential energy. The formula becomes U is equal to mgh in some books. In some books, this distance is called h. You might remember from your high school or your FSC or A levels or whatever, O levels. But now in this book, we are calling this y. This height is called, represented by y. Just like along the horizontal axis, the displacement is being called x. Along the vertical axis, the displacement is being called y. And therefore, instead of h, you have mg y. So this equation is the same like the equation you studied before. Again, this shows that the potential energy depends upon the change of position, which is height, and this is represented by y. So m is a constant, the mass of the body is constant, g is the acceleration due to gravity. This is an example of gravitational potential energy. So this is the formula for gravitational potential energy. ठीक हो गया? सही है?
Yes.
Yes, ma'am.
So you have the definition.
yes ma'am
This is the formula and this is the definition. Okay. Now there are two kinds of energies, potential energies we are talking about. We are talking about gravitational potential energy and we are talking about elastic potential energy. So you remember again from the last chapter that for the case of the elastic body, the equation is half kx squared. We know that k is the spring constant. So the only difference in this case was the fact that the property of this, some springs are very um, difficult to move, some springs are more flexible, some springs are less flexible. This property is represented by k, which is called the spring constant, right? And then it depends upon the distance that has been moved, because in the case of the spring mass system, you move along the horizontal direction in the example that we looked at, and therefore we have x, and we have this equation. We also studied a similar equation in the last chapter, right? So in that case, we were talking about kinetic energy, and now we are talking about potential energy. And this is called elastic potential energy. So if it's in the vertical direction and it's due to gravity, the formula is mgy. If it's due to a spring, then the formula is dependent on k. Okay. And now we come to conservation. Now, as you remember, actually this course is about mechanics. We do have many other kinds of energies, like we discussed the electrical energy, for example. But in this course, we are not going to talk about electrical energy or any other kind of energy. We are only going to talk about mechanical energy. Okay, so that's what we are going to concentrate on. So the mechanical energy is represented by E with a small subscript, E mechanical. Okay, like this. So here you can see this. And it is defined as the sum of the kinetic energy and the potential energy. So this is the mechanical energy. Now, if a body changes from an initial state to a final state, the energy changes, as we have just discussed. Or it goes from state 1 to state 2, again we will say that the energy has changed. So the energy for state 1 will be represented by E1, and for the energy for state 2 will be represented by E2. Similarly, the kinetic energy for state 2 is K2. The kinetic energy for state 1 is K1. The potential energy for state 2 is U2, and the potential energy for state 1 is U1. And therefore, we utilizing the concepts that we just talked about, we know that the change in kinetic energy is equal to work. We know that the change in potential energy is equal to the negative of work. Therefore, kinetic energy is equal to the negative of the change in kinetic energy is equal to the negative of the change of potential energy, because when the potential energy increases, the kinetic energy decreases. And when the kinetic energy increases, the potential energy decreases, and because the sum has to remain constant, it has to be conserved. So if we write this in terms of two states, then it becomes K2 minus K1 is equal to delta K, this one, and U2 minus U1 is equal to delta U. So when we put this value, we rearrange it, we get the equation for the conservation of mechanical energy, which is the sum of the kinetic and potential energies in one state, let's say the second state, is equal to the sum of the kinetic and potential energies in the first state. In some books, this is also defined as the sum of the kinetic energies in the initial state is equal to the sum, and potential energy is equal to the sum of the kinetic and potential energies in the final state. So anyway, it is that in one state, the sum will be the same as in another state. So here you can have this definition in words, and here you can have it in the form of a definition. So this is a principle of conservation of mechanical energy. Okay? Okay? So if this is the case,
Yes, ma'am.
good. So then the change in mechanical energy will be equal to the sum of the changes of the kinetic and potential energies, and this will be 0. Okay, so these are the main concepts and the main equations. Now let us look at an example. A very good example is the example of a pendulum. What is a pendulum? A pendulum is a small mass suspended by a string. Now when it is at rest, we call this the rest position, the mean position, or the zero position, right? when you move it a little bit, it starts oscillating to and fro between two extreme positions, right? So it goes back and forth like this. So when it is here, it starts moving, there is a kinetic energy, but it's also x position. X position goes like this is x, and it's also going upward, so the y position is also changing, the x position is changing and the y position is changing. So you can see that the kinetic energy is changing and the potential energy is changing. So when it reaches a maximum height, we say that the potential energy is maximum. And then when it's coming back to the mean position, अच्छा मेरी बात सुनो, आपने वो same link दोबारा click कर देना है to continue the meeting if it ends. समझ आ गई ये? ठीक है?
Yes, ma'am.
हाँ,
Okay,
क्योंकि
ma'am.
ये मीटिंग जो है ये थोड़ी देर में एंड हो जाएगी, तो आपने उसी सेम लिंक को दोबारा क्लिक करना है, तो यू विल एंटर द मीटिंग अगेन. ओके, सो यू मैक्सिमम जो है दिस विल अगेन चेंज इनटू काइनेटिक एनर्जी, यहाँ पे आके के मैक्सिमम हो जाएगा. फिर ये दूसरी साइड पे जाना शुरू होगा, एंड अगेन यू विल सी दैट द पोटेंशियल एनर्जी स्टार्ट्स इंक्रीजिंग एंड द काइनेटिक एनर्जी स्टार्ट्स decreasing. But at any one time, you will see that k plus u will remain the same. So this is what you have here. For example, in this case, this is the bob is at the mean position and the kinetic energy is maximum. The potential energy is 0 because the sum has to be the same. As this body starts moving upwards, the kinetic energy starts decreasing and the potential energy starts increasing. The sum again remains the same. Okay, then as the body goes higher and higher, it reaches a maximum position. On one end, you see the whole kinetic energy has now been converted into potential energy. ठीक है? So the different stages of this diagram represent how the kinetic energy and the potential energy change back and forth. And you will see that at the maximum height, you have maximum U, like in this case. And at the mean position, you have maximum K. And in between, you have a sum of both. But at the total energy at any one point remains the same. So that was what we were talking about. Okay? ठीक हो गया?
Yes, ma'am.
Okay. Now let's look at. Another thing that we have when work is done, we know that there can be two cases. One, no friction is involved, and two, friction is involved. So in both cases, if there's no friction, you don't have to include friction, and your equation is W is equal to the change in kinetic energy plus the change in potential energy, whereby we can say W is equal to the change in mechanical energy. But if your problem statement says that friction is involved, then you have to include the element of Fk, which is the friction, the kinetic friction. Okay, so in different cases, you can see how this works, and your equation then becomes dependent on FKD, the work done by the frictional force. So the force in this case is small fk, the frictional force multiplied by the displacement that is produced by this frictional force. And this gives rise to a change in energy, which is known as the thermal energy. So in this case, the total work done will be a sum of the change in the mechanical energy plus a change in the thermal energy, because normally friction produces heat. चीज गर्म हो जाती है ना when there's friction. So the equation for work, if there is a frictional force, becomes a sum of the change of the mechanical energy and the thermal energy. So this brings us to the conservation of energy. And we can see that the total energy E of a system can change only by amounts of energy that are transferred to or from the system. So this is the equation where we have included the different kinds of energy that may be possible. So in this case, E mechanical, we're familiar with this. E thermal is any change in the thermal energy of the system, and E internal is any change in any other type of energy that may be present in the system. So the total sum will be delta E, and this will be equal to the work done. So this is the conservation of energy.
Ma'am, what is internal energy?
इंटरनल एनर्जी कैन बी द एनर्जी पोजेस्ड बाय अ सिस्टम. ठीक है, हम इसको ज्यादा नहीं इस चैप्टर में यूज करेंगे. हम ज्यादा मैकेनिकल एनर्जी की ही बात करेंगे और थर्मल एनर्जी की बात करेंगे, लेकिन लाइक देयर आर अदर काइंड्स ऑफ एनर्जी दैट कैन बी प्रेजेंट इन द बॉडी. ठीक है ना, ड्यू टू इफ हम तो बॉडी को ऐसा होल कंसिडर कर रहे हैं ना, लेकिन हमें पता है कि बॉडी के अंदर भी पार्टिकल्स होते हैं. ठीक है ना, तो उनकी भी एनर्जी होती है, उनका भी मोशन होता है, उनका भी सब कुछ होता है. बट वी आर नॉट गोइंग इनटू सो मच डिटेल एट दिस पॉइंट. ठीक है.
Okay.
Okay, right. Now we can look at different examples in this case. Power आपको याद है, it's the same जो पहले पढ़ा था. P average power is equal to the change of energy per unit time. And इसको आप इस तरह से भी लिख सकते हो और instantaneous power के फॉर्म पे ऐसे भी लिख सकते हो. ठीक हो गया? And then we can talk about an example. अब थोड़ी देर में ये मैं अटेंडेंस ले लेती हूँ आप लोगों की, ताकि we can verify who's present. ठीक है, and let's see. Okay, so Abira, let's start with Sarmad. No. Amar, Muhammad Amar. No. Then we have Abu Bakr.
Present, ma'am.
Good. We have Fatima. No. We have Usman, Muhammad Usman. No. Anam Basharat. No. Bilal, Muhammad Bilal.
Yes, ma'am.
Hamza Dar.
Yes, ma'am.
Yes. Fariduddin.
Yes, ma'am.
Kessler. No. Zarish Harun. No. Haris. Muhammad Haris. No. Muaz.
Present, ma'am. Present, ma'am.
Good. Hafiz Ibrahim.
Present.
Good. Acha. Huma Irshad. No. Alina Khalid. Yes.
Present, ma'am. Present.
Hunain, Muhammad Hunain.
Yes, ma'am.
Yes. Rana Shehbaz. Where is Rana?
Yes, ma'am.
Sania Ahmed.
Present, ma'am.
Good. Arisha.
Yes, ma'am.
Okay, good.
Present, ma'am.
Okay. Chand Khushi.
Present, ma'am.
Okay. Maiza Asif. No. Yusuf Patras. No. Abira.
Present, ma'am.
Good. Nadia. No. ये क्या है? हयान अहमद. No. Cheryl. No. Muhammad Ashraf. No. Huda Zahur. No. Amelia.
Present, ma'am.
Okay. Bisma.
Present, ma'am.
Okay. बिस्मा, आपका नाम कहाँ है? हाँ, ठीक है. Okay, so Sadiqullah. No. Sohaib.
Ma'am, present.
Good. Talha.
Yes, ma'am.
Good. And Zulkarnain Ali. Ali Zulkarnain.
Yes, ma'am.
Yes, ठीक है. अच्छा, हमारी मीटिंग अब एंड होने लगी है, तो ऐसा करते हैं कि हम ये मीटिंग छोड़ के तो उसी लिंक को दोबारा क्लिक करते हैं. ठीक है?
Okay, ma'am.
Okay, ma'am.
Okay.
Okay.
Yes, ma'am.